All right, here we have a example of a constant acceleration problem that is not trivial to solve. So it says a train passes me while traveling 12 meters per second and slowing down at 1 meter per second squared. 2 seconds after the train passes, I start chasing it, speeding up at 2 meters per second squared. How fast are we both going when I catch the train? All right, so this is a constant acceleration problem. And one of the things that we see is that constant acceleration isn't really a physics principle or a math principle. It's actually a special case. The equations that we use for constant acceleration are only valid if the acceleration doesn't change. So I'm going to say that we're going to use constant acceleration because we assume acceleration is constant. And this is going to let me use the equation that d is equal to v0t plus 1/2 at squared, and that v is equal to v0 plus at, among other equations. There are actually 4 constant acceleration equations, but those are the 2 that we're probably going to need. Now look, if you put that up here as your physics principle, that's fine, but we do need to make sure that we explain what physics we're using, and in this case, the physics we're using is a set of special case equations that are only valid for constant acceleration. Now, the problem doesn't explicitly say that these things have constant acceleration, so we do have to make an assumption that the acceleration is going to stay constant for the entire time, but we can do that. All right, so when I'm solving constant acceleration problems, the two things, or the place I want to start is to look at what I know. And we've got 2 objects here. We've got a train, and we've got me. So what do we know about the train? We know the train has an initial velocity of 12 meters per second, and we know that it has an acceleration of negative 1 meter per second squared. Now, how do I know the acceleration is negative? I know the acceleration is negative because the train is moving forward and slowing down. So if forward is the positive direction and you're slowing down, that means the acceleration needs to have the opposite sign of the initial velocity. So negative in this case. And that's all we know about the train. What do we know about me? Well, we know my acceleration is 2 meters per second squared. That was given in the problem. It also says I start chasing it. So that is a little subtle, but I think that means that my initial velocity is 0. Now, this is where explain part C comes in, because the problem did not explicitly say that my initial velocity was 0. So how do I know that it is? Because I started chasing. And to me, that means I wasn't already running. I was just standing there. So this is the kind of thing that we have to read the problem carefully. If the information's not given explicitly in the problem, we have to sort of explain why it is we are using that number. And initial or final velocity of 0 is a really good example of something that might not be given explicitly, but the context clues are there. All right. Now, the bad news is I only have 2 pieces of information for the train, and I only have 2 pieces of information for me. If I had 3 pieces of information, then we could plug into the constant acceleration equations and find the other 2. But I don't have 3 pieces of information. I only have 2, which means I'm going to have to be tricky. So what else do I know? The 2 other things I know is that the displacement of the train and the displacement of me are the same. So displacement 1 is going to equal displacement 2. The displacement of the train is going to be the same as my displacement. So that seems important. The other thing I know is that the time for the train is equal to the time for me plus 2 seconds. I didn't start running until 2 seconds after the train passed me, so the train is going to be moving for 2 seconds more than I'm going to be moving. So I'm going to use those 2 pieces of information to solve this problem. And I'm going to start with the fact that we know the distances are the same. So the distance for the train is going to be, and I'm using this equation right here, the distance for the train is going to be 12 meters per second times t plus 2 minus 1/2 times 1 meter per second squared times t plus 2 squared. Okay, and I took the minus out. The acceleration was -1, but I just put it out in front of the 1/2. Okay, and we know that distance 1, or distance 2, the distance that I travel, my initial velocity was 0, so all I have is 1/2 at squared, so that's going to be 1/2 times 2 meters per second squared times t squared. Now notice I put in t plus 2 for the train, and I put in t for me, and that's because we know that the train is moving for 2 seconds more than I am. All right, so now we're going to set these things equal to each other. So this is going to equal that. All right, so for d2, I get just t squared. Because 1/2 times 1 gives me 1. And on the right-hand side, and now I'm going to drop the units. On the right-hand side, I get 12t plus 24 minus 1/2 of, and now I'm going to take the t plus 2 squared, and that gives me t squared plus 4t plus 4. Remember how to do squaring a binomial. You do not just do t squared plus 2 squared. That doesn't work. All right, so let's try to simplify all this. This gives me t squared equals, well, let's just go ahead and keep the 12t and the 24. And then I get minus 1/2 t squared minus 2t minus 2. So this 24 and this 2 become a 22, and this 12t and that 2t become a 10t, and I still have the 1/2 t squared, so this gives me 1.5 t squared minus 10t minus 22 equals 0. Now that is a quadratic equation. And so we can do minus b plus or minus square root of b squared minus for a c 4AC, that's 4 times 1.5 times 22, so that's 132. Right, but it becomes a plus because minus 4AC, but C is negative, so 4 times 1.5 times 22 is 132, divided by 2A, that's 3. And when we plug this in, we find out that our times are equal to either negative 1.74 seconds or positive 8.41 seconds. Now, negative time means before the problem started, and that's not really a useful solution for us. The positive time is the one that makes sense. So now that we have the time, one thing I want to do is come back up to D1 and see how far it actually went. So if I do 12 times 10.41 minus 1/2 times 1 times 10.41 squared, I get about 70.7 meters. And if I do 1/2 times 2 times 8.41 squared, I get about 70.7 meters, and that's good. It means that I went the same distance. Both the train and I went the same distance. But that's not what the problem asked for. What the problem asked for was how fast we were both going. So the train's velocity is going to be 12 meters per second minus 1 meter per second squared times 10.41 seconds. Why 10.41 seconds? Because t plus 2. The train was going 2 seconds longer than I was going. And if you plug this in, you get the velocity of the train is equal to 1.59 meters per second. It has almost stopped. Okay, and my velocity, v2, is going to be v0, which was 0, plus 1/2 times acceleration times time squared, and that gives me a final velocity of 16.8 meters per second. Okay, so finally, we want to evaluate the answer. Put your answer into context by comparing it to an appropriate reference value. And it says if the problem has multiple parts, pick just one. So I'm going to pick my velocity. My final velocity of 16.8 meters per second is faster than Usain Bolt's world record 100-meter dash of 12 meters per second. Now, why is that useful? It's useful because we want to be able to compare our answers to something we can visualize, to something that we understand, and this is a great comparison because Usain Bolt is the fastest man alive, and he ran at 12 meters per second. So this problem says I was running at 16.8 meters per second, which is silly. There's no way I can run that fast, so the problem is actually impossible. I would not have caught the train in 70 meters, and I would not have been able to continue accelerating 2 meters per second for the entire time, 2 meters per second squared the entire time. You don't have to write any of that in your evaluation, but what the evaluation does tell us is that the problem doesn't really make sense. That's fine. I made up this problem for today's example. The fact that the answer doesn't really make sense is no big deal. I just wanted to show you how to do a complex constant acceleration problem.